Right, let's start again on functions. Now in a much more formal setting, we have some ideas about functions having been input-output boxes. Let's start to get into the nitty-gritty now. So f of x, the typical way we write a function is f of x, and I'm going to start with an example. For instance, f of x equals x squared. Now let's look at the various parts of the function. This f is the name of the function. Okay, let's say it's the name of this function. Now it doesn't have to be f, it can be any letter. For instance, we could have g of x, right, equals x cubed. Is also a function. So this is the name of the function, this letter here. Okay, this is the input that we keep talking about. We have talked about before in other videos. So this is the input to the function, and this here is the output. This is what it produces. Okay, so here in this case, this is the output. This whole thing, this is the output, and this whole thing, this is the output in this case. So when you see a function, first of all, you need to understand how they work. This is how you take them apart. F of x equals x squared, or g of x equals x cubed. A function formally, what is actually happening is a function takes an input and maps it onto an output. A function basically takes something here from the domain, okay, and maps it onto the codomain, which we've also called range before. Okay, so basically it takes something from here and maps it into this other place. Takes something from here, maps it into this place. Okay, so this is where your x usually is, and for instance in this case this would be x squared for that first example that we had. Okay, so if we had the number 1 here, it would be mapped to 1. If we had 2 here, 2 squared is 4, and so on and so forth. Now when we have to start thinking about these mappings. Now what's actually going on? More formality. We need to learn more language, more of how we actually define functions. So what's actually going on is, what's the domain of this function? So what we're saying is we're going to take real values and map them onto real values. But one thing we do know about the squaring function, okay, is it only produces positive values. There are no negative values. So you go from all real numbers are mapped to all real positive numbers, for instance. So this is how a function basically maps, okay, input to the output. It's still the same thing, okay? It's still the same thing. This is the input. The domain is the input, remember? And the codomain or range is the output. But now we're starting to formally define more properties of these of the domain and the range, or the domain and the codomain. Okay, is that the domain is all real values, codomain is all are positive. Okay, these are different sets of numbers. Right. Let's go on. Now we come to what's a very important topic, which is function evaluation. Okay, so evaluation of functions is very important. I've been actually doing that, assuming you understand it, but here now I will give you a formal explanation of what I mean by evaluating functions. So evaluating functions, what does that mean? Okay, so let's talk about evaluating functions. When we say we are evaluating a function, we mean, okay, let's go back to the fx equals x squared. What it means is that when I put values in here, like x equals 1, it means f of 1. Replace every x you see with a 1, and that gives me just 1 squared, which is 1. Now similarly, if x was 2, or let's say x was 5, we get f of 5, which means we're going to take 5 and square it, and that gives us 25. Okay, let's move to another example. Say f of x equals x squared plus 1, for the sake of argument. Now this is where the confusion starts to begin. When there are more things than just the x present, When you're evaluating a function, same thing happens. When f of 2 now means x is going to be 2. So this is the only place there's an x. That's just a constant. So you just copy that down, do nothing to it, and essentially the result becomes 5. So here's another, if we calculate f of 3, that would be 3 squared plus the 1, and that will give us 9 plus 1, 10. So it's pretty straightforward, nothing very complicated, but still, I'd like to mess with something a little bit more. Let's get a little bit more advanced. So here's x squared plus 3x plus 7. Now let's try to evaluate this one. So f of 2 would be 2 squared plus 3 times 2 plus the 7. Remember, no x here, so the 7 is a constant. So we don't do anything to it, we just copy it down as it was. And that means we get 2 squared is 4, plus 3 2s is 6, plus 7, so that gives us 17. Another one of this, f of 4, for instance, is 4 squared, plus 3 times 4, plus 7, that gives us 16, plus 12, plus 7, that gives us 35, okay? So that's how we actually evaluate functions, which is basically finding the value of the function. In other words, evaluating means what is the output. I'm going to give you an input, now tell me what the output is, okay? So essentially it's saying, here's a number, I feed it into the function, what is the output from the function, okay? So let me just reiterate that in terms of the box idea that we've looked at. So here the function is this one, for instance, if it was the x squared plus 1 function, and then what we're doing is we're feeding a, for instance, a 2 to it. And what does it give me? When I feed a 2, it gives me 5. When I give it a different input like a 3, it gives me back a 10. Okay, so now you see, I hope you understand what we've talked about before as functions being input-output boxes, okay, that take an input and give us an output. Now remember, mathematically, of course, when we talk mathematically, we're talking about functions that take numbers at input and give output as numbers as well. But something interesting, something fun, something complicated sometimes is happening to these functions. Now functions aren't only just x's and y's. This course is basically a calculus course, calculus 1. So you already have some knowledge of functions, and you've heard of things called trigonometric functions. Okay, trigonometric functions, the log functions, the exponential functions. We'll come to these a little bit later. But anyway, here's some basics of evaluating a function. Okay. So now if we come to the definition of function, a function, if we talk about a definition, something that is a valid function, I'm going to show you figuratively how it works from this diagram. So here's f. If it is a valid function, you can have, for instance, 2 different values mapped to the same value. No problem there. Okay. But what you cannot have is the other way around. In other words, we cannot have, let me show you here in a different diagram. Let's change the color. So, for instance, you can't have this happening. So you can't have the same value mapped to 2 different values. Okay, this is not allowed. This is not a function. Not a function. Okay, one value can be mapped to only one value. Now it's no problem if 2 different values from the left side or from the domain are mapped to the same value on the other side, in other words, on the range or the codomain, but not the other way around. So this is a very important property, and the one key property that defines a function. All right, that's basically the definition of a function. For instance, if we look at the function f of x equals x squared, now if we look at them from a mapping perspective, f of 2, okay, 2 is mapped to 4, and minus 2 is also mapped to 4. Now that's valid. So f of x equals x squared is a valid function. Now, other formalities that you should be familiar with is that many times we use the letter y in this format. For instance, y equals f of x. Okay. Now we could easily say, for instance, when we say f of x is, for instance, as we used before, let's try something new. Say x to the 5. Then we can say y. We can also say y is equal to x to the 5. Now you must understand that they mean the same thing. Okay. Where now y is the output, okay, and x is the input, okay. So this is just another way of writing it, and we'll see this quite commonly used in Calculus 1, where and sometimes interchangeably used. The other formalities you need to be familiar with is, you see here, there is a relationship between y and x, and this is a dependence relationship. Now, if you look at y, do you think y can survive on its own or can be defined on its own? No, it needs x to be defined, but x doesn't need anyone to be defined. So we call x the independent variable, okay, and y is called the dependent variable. Okay, remember this. Now what we're trying to build up, remember these are some preliminaries that we're trying to build up so that we can get on with doing some calculus. So x is an independent variable, y is a dependent variable. So, but x is still the input. The same concepts, same ideas apply. Okay, but now we can, for instance, construct a table of values where here's your y and here's the x. And you can have, when y is 1, x is 1, x is 1, y is 1. When x is 2, y is 32. And when x is 3, y is 243, and so on and so forth. Okay, so but this is, of course, this is related to this definition here. So you've seen this before, and then we come up to this, which is the Cartesian coordinate system. Now the Cartesian coordinate system is basically trying to draw functions. So the x is always along the horizontal traditionally, and y is along the vertical traditionally. The vertical axis is y, the horizontal axis is x. So, but y here is, we can also use f of x here. So interchangeably, as I said, both can be used. Now, you see, you can take this pair of values 1, 1. So here's 1 and here's 1, and we plot the value here, and we get this, another way of representing these things now in terms of a graph. The value is 1 and 1. Now if you go to the number 2, for instance, it's 32. Oh, it jumps up somewhere here, for instance, for the sake of argument. So there it is, 2 and 32, and so on and so forth. And then you can start connecting these and form graphs. So very quickly, what I've tried to do here is to familiarize you with the various notations that are important when we deal with functions. Concept is still the same. I still want you to remember that function is an input-output system. Any system can be represented that way, that has some form of input and gives us some output. Usually these are measurements, and in mathematics we usually stay in the mathematics that we're dealing with right now. In calculus, we're going to be looking mostly at functions that take numbers, input as numbers, and numbers as input, and give us numbers as output. So those are some other terms that you need to familiarize yourself with as we progress through this this particular course. Okay. Now this thing here, these things, they're called ordered pairs. So more ordered pairs. Again, as I said, this is a primer, so I'm trying to get you back into understanding some of these terms, and we may use these later on, but this is a well-known term. These are called ordered pairs. Now when you go later on in Calculus 3 and look at 3 dimensions, there'll be ordered triples, okay? Usually spatial variables go up to that level, and that's about it. That's where we stop. Okay, so I think we've covered almost everything there is on the basics and some formalities of of functions. A one-to-one function, okay, is one that, if we look at the diagrammatically, once again, it becomes very simple to look at. So this diagram, which is a valid function, and here's another one. This is also a valid function, okay? Now, this is a one-to-one. This is called a one-to-one function. Okay, I'm going to use this letter Fn is to represent short in short form. Here you see what's happening. What's the difference between these two diagrams? Notice that here there's a value that's mapped onto this, and this value is also mapped on the same number, and this value is mapped onto a unique number, whatever. But the thing is, these two numbers are mapped onto the same value. Now, when a function is one-to-one, each value on the domain is mapped to a unique value in the range or in the codomain. So each one value is mapped to a unique value in the codomain. Such a function is referred to as a one-to-one function. Here's an example: f of x equals the simplest function x. So every value, for instance, here let's look. 1 is mapped to 1. 2 is mapped to 2. 3 is mapped to 3, and so on and so forth. So no two values on the domain can be mapped to the same value in the codomain. It's not possible. Okay, so such a function is called a one-to-one function. Okay, but if I were to look at another example here, for instance, if I were to look at fx equals x squared, okay, quickly again, let me draw it this way, as visually it's easier to see sometimes. So 2 is mapped to 4, but you see minus 2 is also mapped to 4. 3 is mapped to 9, and so on and so forth. Okay, but you see that? That 2 and minus 2 are both mapped to 4. So what does that tell you? Is x squared a one-to-one function? Of course not. So this is not one-to-one. Okay, and this one is one-to-one. So I hope that's clear as to how functions are one-to-one. The final concept we want to quickly look at on the preliminaries on functions is the inverse of a function. Okay, so an inverse of a function is basically reversing. It's reversing the effect, okay, of a function. Okay, so reversing the effect of a function. So for instance, if I had a function f of x equals 2x, that means I'm doubling the function. What's the reverse of that? I mean, what is the reverse of that? The reverse of that will be having the values. So if I give it input, it doubles it. Now if I want my original value back, I have to take the half of it, right? And then I'll get what I started with. For instance, if I were to f of 2 is 4, okay, but then what was the original value that I put in? I take half of 4, and that gives me 2. That gives me the value back. So in the inverse concept of the inverse is basically trying to reverse the effect that the function had. So in other words, basically what you're saying is, if we look at it from an input-output perspective, so you gave it input and it gave you output. Now, what if you had the output and you wanted to know what was the original input? Okay, in fact, you know what? That's the basics of reverse engineering, is you take the output and you try to figure out what the input was. Okay, what input gave you that output? And the basic idea, that's the basic idea of the inverse of a function. Now, formally, the inverse of a function is only possible for one-to-one functions. In other words, the formal definition is a function f has an inverse if and only if it is one-to-one. So, formally, a function f has an inverse if and only if it is one-to-one. If it is one-to-one. So that's very important to state here, if it is only one-to-one. And the reason for that is quite simple. Let's have a look. So, now that you understand a function is for reversing, that means that what you're doing is a function f does this. Okay, so it maps things from the domain onto the range. Okay, so that's what it's doing. Let's put arrows here to show what direction. Now the inverse is symbolically written like this with a -1 up here. So it's f inverse of x. That's how we symbolically write it. So the inverse function, in other words, is going to say, I mean, if I take the same 2, so the inverse would mean it's going from here, okay? So it's mapping things back from the range back to the domain. Now, try to understand. If the function was not one-to-one, let me explain. This is a one-to-one function here. This is a one-to-one function. However, here, let me show you a function that is not one-to-one. Now, notice the problem in this case. If I were to try to go back, in this case, from one value to 2 values, what would be the inverse function then? What would be the inverse? It would not be a valid function, of course. So the function would be invalid. So you can't have, it's f inverse, not a function now. You see in this case. So you can't have this side. You can't have this side. Okay? So that's why a function has to be one-to-one for its inverse to exist.